Welcome to this explainer. So imagine for a second you are trying to build a massive suspension bridge, or maybe a commercial airliner. You wouldn't just start welding steel together and figure out the physics later, right? No way. Well, back in the early days of software engineering, developers felt that exact same urgent need to avoid chaos. They needed a way to plan everything in advance, to treat software with the very same rigorous, structured predictability as physical engineering. Today, we're exploring one of the absolute most famous and heavily debated frameworks in software history, the Waterfall Model. To really wrap our heads around this model, we've got to look at the core problem it was originally trying to solve. How on earth do we bring order to the chaos? You see, before this framework existed, software development could easily devolve into an uncontrolled, unpredictable mess. Programs were getting way larger, teams were growing rapidly, and the stakes, well, they were getting much higher. The industry desperately needed a roadmap that could provide stability, control, and organization to a process that naturally tends toward complete chaos if you just leave it unchecked.
Okay, let's dive right into this. Here is our roadmap for today's explainer. First, the origins of waterfall. 2, phases of the cascade. 3, the V-model variation. 4, strengths of the model. 5, weaknesses and criticisms. And finally, 6, when to use waterfall.
All right, Section 1. The origins of waterfall. Now, this model didn't just appear out of thin air. It was a direct reaction to the early, kind of Wild West days of computing. The very first published model of the software development process came from a man named Winston Royce back in 1970. Because early software pioneers were mostly working right alongside hardware and systems engineers, they observed how those massive physical systems were built. They basically borrowed the plan-driven sequential frameworks used in hardware to try and bring predictability to coding. The idea was super simple. If a systematic, linear approach works for building complex physical machines, well, it should work for building complex software too. But you want to know the ultimate irony here? Royce actually warned in his original paper that a strict single-pass linear approach was incredibly risky. But the industry just loved the simplicity of his linear diagrams, and they ran with them anyway.
And that brings us to the name itself, as our source material notes. Because of the cascade from one phase to another, this model is known as the waterfall model. Really think about that metaphor for a second. Water only ever flows downward, right? It has this inevitable gravity-like flow. Once water spills over the edge of a rock, it absolutely doesn't flow back up. And this perfectly illustrates the rigid, strictly linear nature of this entire engineering process.
Moving right along to Section 2, phases of the cascade.
So what does this downward cascade actually look like in practice? It basically features 5 principal stages. It starts at the very top with establishing exact goals in requirements definition. Then it cascades down into design where the whole system architecture is established. From there, it drops down into implementation and unit testing, which is where the actual code gets written. Then it flows down into integration and system testing to ensure the whole system meets those initial requirements. Finally, it pools at the very bottom in operation and maintenance. The absolute crucial rule here, it is a strictly plan-driven process. You must completely finish, document, and totally lock in one step before spilling over into the next. You finish requirements completely before you ever even think about design.
Section 3, the V-model variation.
You know, the classic life cycle wasn't just entirely static over the decades. It did evolve. Engineers pretty quickly realized they needed a much better way to conceptualize testing within this super strict framework, which led to the V-model. This variation visually depicts exactly how quality assurance actions map directly back to the earlier engineering actions. See, in the classic waterfall, testing is all essentially grouped together at the very bottom of the cascade. The V model was a direct response to ensure that verification isn't just treated as a complete afterthought at the end of the line.
To really picture this, imagine taking that linear downward waterfall and physically bending it right in the middle to form a V. As a software team moves down the left side, they're progressively refining basic problem requirements into detailed technical designs, and then finally into code at the very bottom point of the V. Then the team moves up the right side, and as they move up, they're executing tests that directly validate the precise models and requirements they created way back on the left side. So unit testing verifies the detailed design, system testing verifies the architectural design, and acceptance testing verifies the original user requirements. It creates this really perfect closed loop of accountability.
Section 4, strengths of the model.
Why did this rigid, plan-driven process absolutely dominate software engineering for literal decades? Well, the benefits, especially from a project management perspective, are pretty massive. First off, it's entirely consistent with traditional physical engineering, making it extremely familiar to large legacy organizations. Second, it offers incredibly high process visibility. Because extensive formal documentation is produced and literally signed off at each specific phase, managers get regular, concrete milestones. When the design document is officially approved, boom, you have achieved a definitive milestone. You always know exactly where you are on the project timeline.
Section 5. Weaknesses and criticisms.
Now, what's really interesting about this next part is that the industry eventually learned some very hard lessons. As our source material points out, this premature freezing of requirements may mean that the system won't do what the user wants. Because iterations and having to rework things are so heavily penalized in a downward-flowing model, it basically becomes standard practice to freeze parts of the development super early on. But here's the reality. In a fast-paced, fluid, modern business environment, customers rarely know all their technical needs on day one. If you lock them into a rigid contract immediately, you run the very real risk of flawlessly executing the perfectly wrong system.
Building on that core flaw, this inflexible partitioning into distinct stages makes responding to changing customer needs incredibly difficult and honestly really expensive. Furthermore, actual working software isn't even available until very late in the project timeline. So think about this. If you made a major blunder during the requirements phase, let's say a fundamental misunderstanding of what the database needed to handle, it might remain completely hidden until late-stage integration testing, right before the product is supposedly ready to ship. Discovering a disaster that late, it is incredibly costly.
Which brings us to Section 6, when to use Waterfall. So, hearing all that, you might be wondering, does this mean Waterfall is entirely useless today? Actually, scratch that, not at all. It simply has highly specialized modern use cases. For safety-critical or heavily embedded systems, like say an aircraft flight control system that might take up to 10 years to build from initial specification to deployment, you absolutely want a strict, plan-driven waterfall approach. You need exhaustive analysis, rigid planning, and literal zero-defect execution. Conversely, for a fast-paced business or e-commerce web app where market conditions change daily and you desperately need iterative user feedback, the heavy documentation overhead and just the sheer inflexibility of Waterfall, that would completely crush your ability to pivot.
And this brings us to the ultimate takeaway from our deep dive today. At the end of the day, software engineering is all about choosing the right tool for the job. You must dynamically match the process model to the specific scale of your project, the inherent level of uncertainty in what's required, and any external regulatory demands. Generally speaking, successful engineering requires finding a strategic balance between plan-driven approaches, like Waterfall, and more flexible, agile processes. There simply is no single, magical ideal software process that works perfectly for everything.
So, I'm going to leave you with this question to chew on. Will your next project be a bridge that requires a rigid blueprint, or a startup that demands rapid agility? Properly evaluating your project's unique landscape is the very first and perhaps most critical step in software engineering. Thanks so much for joining me for this explainer on the waterfall model.